Don't answer that. All right. So this should work. Famous last words. And again, part one is a lot of stuff that you already know. By the way, anytime you see anything on my screensaver, I took it from my camera. I took that picture. My husband's like, because I dabble with astrophotography. He's like, you should make those your screen or your desktop. So they're all my pictures if you see them. All right, let's duplicate these. Oh, is that what I want to do? I think. All right. So you know that pure substances can either be an element or a compound, and we use formulas to make this. I just love the conciseness of chemistry in general. We use formulas to represent compounds. Of course, the number of atoms of each type of element are the subscripts, not superscripts, subscripts. We're not in here necessarily going to see the atom, even though when we met last time on Wednesday, we actually saw copper kind of using a scanning tunneling electron microscope, I think it was, to see a copper atom. But instead we have this sort of visualization where these first four are pure substances. The color, they're all the same type of atom. And then we kind of switch gears over here. These are compounds. So one thing about it, we're going to be doing some of this in the chem lab, is you can take something that's a compound, which is more than one atom, two or more atoms of different elements that are joined together. And you can, like if these are my two atoms, I can break that chemical bond. Okay, that's a type of what we call decomposition reaction. In doing that, okay, I still have the atoms that I started with, but they're no longer connected. Okay, I have not split the atom. The opposite of breaking a chemical bond would be splitting the atom. These are what we call, when we break a chemical bond, those are ordinary chemical reactions, and that's all we're going to do this semester. Kind of if you look across what we're starting with, and I don't know if you can tell or not, but we start with MgO, magnesium oxide. We heat it up, it breaks the Mg and the O bond, and we end up with, it's not magnesium oxide, it's mercury 2 oxide. What does mercury look like? Just the element mercury.
And like silver.
It's like silvery. It's like one of the two liquids that are elements. Yeah, so we end up with kind of this liquidy silver over here. This is the silver 2 oxide, which is like a solid. One of the things that you're going to want to be able to do, I believe in your homework, is to identify that some sort of chemical reaction has happened. In general, chemical reaction just means that you start with something, okay, and then after the process, you have something else. In this case, we can tell that we started with mercury 2 oxide, okay, and we ended up with liquid mercury. Where'd the oxygen go? In the air. Yeah. If I were to animate this, we would actually see that oxygen just kind of flew off. So, guess what? Does this make sense? This should weigh lighter. We take advantage of that in the chem lab, and this should be heavier. Because why? It's got oxygen. This is just the okay. Now, I told you I'm kind of trying to streamline things, and I'm not going to play these little videos. This isn't a video, but it kind of is a picture that you guys maybe already noticed. You can take water and run a current for H2O, and that actually will break the hydrogens off of the oxygen. That's exactly what's being done here. I know they dabbled with, maybe that's a way that we can, like on the moon, like there's water on the moon, and maybe we can take liquid water, or liquid solid gas, and electrify it, which takes some energy, and get our hydrogen, and then we have a fuel to use on our moon base. It's been a while since I heard that. Actually, I think George Bush Jr. thought of that, so he wasn't a scientist. But anyway, so you can see the water, the electric current. Check this out. How would you describe, this is the water, it's not water. This is the gas that's being collected up here. So we're taking H2O, breaking it apart, and I'm not even going to answer the formal question. But you would tell me H2O1 is the formula for water, H2. So there are 2 hydrogens, so you can kind of see them over here, twice the volume, for every 1 oxygen. So that's not an accident, that's the way it works. I love science and chemistry, because you're like, wow, it makes sense. Because one of the things about gases is if you have the same number of gas particles, regardless of its hydrogen, oxygen, nitrogen, carbon dioxide, they will all occupy the same volume if they're the same temperature and pressure. So just kind of a sidebar. This is showing you the same thing. This is called the electrolysis, because we're electrifying water, electrolysis of water. You start out with water and you get your elements back. Remember, compound and elements are all types of pure substances. All right, notice I have skipped next 5 slides. So if you're kind of a slide counter, we're going to skip the next five slides because I'm going to go into this in more detail later. But this is how it works. So matter can either be pure or it can be a mixture. And if it's pure, it's either an element or it is a compound, CPD. Mixture, of course, we have homogeneous and heterogeneous. You know the rest of these words. My point here is with regard to compounds, we have 2 types of compounds. We have molecular compounds and we have ionic compounds. And we will talk more about that distinction. I just kind of wanted to show you on the flow chart where it all fits in. Okay, again, just kind of hitting things that you already know. We're going to take a look at something that you already know. Discounting the physical phase of plasma, the normal physical phases, matter can either be in its solid state, its liquid state, or its gaseous state. Again, I'm introducing the topic and we'll be talking more about that. But, well, let me say it here. What keeps matter together, whether that matter is either an element or a repeating unit of compound, what keeps that matter together are what we call intermolecular forces. And you're going to see it on the slide coming up, so you don't have to jot that down. But if matter is in its solid state, what we're going to see here on a little grid, if it's in its solid state, we have a lot of intermolecular bonding, okay? And all matter has motion, that's coming up on slide 2, but the motion is just like what we'll call vibrational motion. If matter is in its liquid state, it also has intermolecular bonding, but they're a little more hit and miss. We have some broken things, if you want to, that's kind of what gives it its fluidity. My favorite thing are gases. So if it's matter in its gaseous state, it has no intermolecular bonds. So with that kind of approach or whatever, we kind of have some outcomes of that. This is showing you matter in its gaseous phase. This is water in its solid phase. And this is water in its liquid phase. Now, I think this is right. Water is unique. And can you see where in its solid phase that water looks like it's got some holes in it? I call it fluffs out. It fluffs out. So as water goes from its liquid state into its solid state, it actually expands. We know this because this is why you don't put a can of pop in the freezer. Okay, because pop is mostly water, and as it transitions from a liquid to a solid, it fluffs out. Okay, so that's kind of what we have going on there. This video shows you something. It's like which came first, the motion or the intermolecular bonds? Let's see if this will work for us. It's like a 13-second, if that, video. Blink and you'll miss it. It's favorite ones. I just have to keep replaying it. So you see and I already told you that solids have the most amount of intermolecular bonds and gases have none. So to me, the intermolecular bonds and the motions kind of go together. You know, does it, for instance, if we pick on gases, does it have all that motion because it has no intermolecular bonds? Or does it have no intermolecular bonds because it has all that motion? Which came first, the chicken or the egg? And I'm not here to decide that one for you, but that's the situation. So we kind of have a couple of things. These last 2 columns, degree of intermolecular bonding. Okay, I'll talk about that. Solids would have what? Most. Gases have least. Over here, this last column, with regard to which one would have the most kinetic energy, most motion?
Yes.
Gases. Yep, solids have least. This one, this first column, is a little different. And it makes sense if you think about it in terms, I think, of both its intermolecular bonding and its kinetic energy and motion. So, for instance, solids, guess what? They have a definite size and they have a definite shape. A little bit ago, we saw an Erlenmeyer flask with a block in it. You're like, dude, it's a block. It's going to keep that shape, keep that volume. Well, liquids, guess what? They have a definite size or volume, but a liquid will take on the shape of its container. Okay, well, that's kind of fun. What about gases? What about its size? Indefinite, yeah. It'll like expand to take on both the volume and the shape of its container. Yep. So, I kind of like, like the story of Goldilocks and the Three Bears. The stuff that's in its liquid phase has some intermolecular bonding and an intermediate amount of kinetic energy. So, okay. So we've been talking about these intermolecular bonds. Okay, they could be forces that connect ions. They could be forces that connect molecules and ions. They could be forces between molecules. All intermolecular bonds. So, in general, and this goes for intermolecular bonds and chemical bonds, but a minute ago I said if you have a water molecule, you can take it and you can whack the bond between the oxygen and the hydrogen, whack the bond between the oxygen and the hydrogen. It took energy to break those bonds. And so similarly, if I have a water molecule connected to a water molecule connected to a water molecule with intermolecular bonds now, I can whack them and break them apart and take energy. Now, granted, based upon what we were just talking about, does this make sense? That if I go from a solid to a liquid to a gas, okay, going this way, I am breaking intermolecular bonds. I'm breaking intermolecular bonds and I'm giving the cute little matter more kinetic energy. I'm doing both.
And do you break it with temperature?
Temperature is a good way of breaking it. Like in the case of electrolysis, it's electricity. But temperature, thermal energy is the very common way. Exactly. Yeah, but electrolysis was breaking the chemical bonds. These are intermolecular bonds. Very good. So breaking bonds, I'll put E for energy in. Energy in. Now, we'll talk more about this later too. If I go from a gas to a liquid, I'm going to form intermolecular bonds. And if I go from a liquid to a solid, I'm going to form intermolecular bonds. Forming ion bonds. And in this case, energy is going to be released, energy out.
So when you talk about intermolecular bonds, is that like one H2O
Yes.
and another H2O?
You got it. Yep, one H2O and another H2O. And I usually draw it with a dash. I do. I don't think I've ever seen anybody else do it, but exactly what you're saying. And the way it works, and some of you already know this, these are two cute little water molecules minding their own business. And what will happen is between the oxygen of one atom and the hydrogen of the other. So I'll go dot, 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 dot. So that is my ion bond. Exactly. You got it. All right. What else we got? Properties. Remember I said don't taste anything in the camel. I mean, that's a property. It can help you to identify it. We have chemical versus physical properties, and then we have intensive versus extensive properties. I already talked a little bit about a chemical reaction. Remember when I stood up here and I said, if you start with something and you end with something, you've got something after you're done with the process, that means some sort of chemical change has happened. So that's right here. Chemical properties are measured when a chemical change has to be applied to that substance. It's called what we call a destructive test. If you're sending away a sample to a lab for analysis, you might have analysis, a whole list of things. Some of them are not destructive, physical tests, and some of them are destructive. Of course, they're going to do the physical test first, and then the chemical test, which will be different. Which reminds me, I sent in my DNA the other day, and my kids are like, "Are you serious, Mom?" So now they like, we can't do any sort of, like, we can't kill anybody because they have your DNA. So, I don't know. I don't know, that's probably destructive. So, new substances are formed. And you might be like, I'm not sure if new substances are formed or not. In the case of the mercury 2 oxide and the liquid mercury, we saw solid mercury 2 oxide go to liquid mercury. We could actually see at room temperature they were in physical phases, so it's different. This is another example of that, so that would be chemical change, chemical property. So this is actually chemical change too. If you're like into machinery, that might be really sad. But this is just rust. Rust, anybody know what rust is? See on there? It's just iron oxide. There's iron 2 oxide. So here we have, this doesn't look like iron to me, but I'll go with it. So here we have iron, oops, sorry. And here we have iron oxide. So that is a chemical change has occurred. And so does this make sense that a chemical property of Fe, a chemical property of iron, is that it will undergo what we call oxidation? Does everything oxidize? Paper doesn't rust. Paper doesn't oxidize. So that chemical property of paper is it does not oxidize. Chemical property of iron is it does oxidize. See how that works? Chemical property and chemical change definitely go together. These are all physical tests for physical properties. So these are all physical. And the thing about physical is you have the same substance before and after the test. Color, it's important, okay, but you have the same stuff when you gauge the color before and after. The density, like how kind of fluffy or compact it is, that's a non-destructive test. Physical properties or tests are non-destructive. Sometimes this will throw people off because, like, for instance, we'll take an ice cube and we'll see it change phase and you're like, all right, that totally looks totally different. Went from a solid to a liquid, kind of like we saw that mercury 2 oxide go from mercury 2 oxide to mercury. But how do I say this? Could you get your ice cube back? Yeah. Another probably even better way to look at it than that is if I were to be able to look at the molecules on the repeating unit. I have H2 over here, solid state, all stuck together with intermolecular bonds. I have H2 over here in its liquid state. Okay, less intermolecular bonds. So it's still H2. So that kind of throws people off sometimes. Physical properties, does it conduct electricity? Malleability and ductility, that kind of is usually associated with metals. Can you flatten it out? That's malleability. Ductility, can you draw it into a wire? Viscosity is how thick it is. Non-destructive test. This is showing you a non-destructive test. This is just kind of a simple check. What temperature does water boil at on the Celsius scale?
100.
100, very good. So this water bath is 100 degrees Celsius. And here we have 2 white powders, A and B. One powder will kill you. Naturally, I think if you ate too much, it would just vomit probably. And one powder will make your headache go away. Okay. So quite cleverly, what they did was they made a use of the fact that one melts at 80.2. Okay, so that, and I have to concentrate on melting point temperature. So since that's lower than your water bath, that's lower. This one over here, it's not going to melt until 135. So 100 didn't melt. That's quite clever. So you know which one to take for your headache. Clever, clever, clever. Movie. So I think you have the answers to these. Again, look for whether it's destructive or not. Gauging the color, physical property. If something is oxidizing, which is what happens when rust is formed, iron is transformed. The word transformed should give you a hint. That's a chemical property. Not everything rusts. Dynamite can explode. Now here's an example of, after that dynamite explodes, can I take all the things that made that stick of dynamite back? It's like Humpty Dumpty. Can I put it back together? And the answer is no. Chemical changes have occurred. So that's an example of a chemical property. Very good. Density. Well, you guys are going to be doing some densities in the lab, and all you're going to do is be taking a mass in units of grams and a volume. In this case, it's cubic centimeters, but it could be milliliters. And you're just going to take a division. Okay, so non-destructive test, so that's a physical property. I already told you the melting, if you melt something, you're not changing what it is. So that's a physical property. Color again, physical property. Okay, now this one you may not have been exposed to as much. If I start with intensive properties, I usually think of independent of amount. Oops, AMT for amount. Intensive or independent of amount. So an example of an intensive property, well, we can pick on density, intensive property. So like if I'm dealing with water, it has a certain density, and it's kind of a cool density. Oh my gosh. Around 4 degrees Celsius, the density, and we use this symbol for density, is 1.00 grams per milliliter. That is for water. So I'll put a little subscript H2O there. H2OL, because its density changes at different temperatures, different phases. My point's going to be, if I have a cup of water at 4 degrees, or if I have a bathtub full of water at 4 degrees, it's going to have that same density. It's independent of amount. Okay. A property that's independent of amount is the chemical property we just talked about, iron. Iron rusts. Iron will transform from iron to oxide. Does it matter if I have a little block of iron or if I have a whole car of iron? Nope. It's an intensive, independent amount. So the opposite of intensive is extensive. And so extensive does depend upon amount. Does depend upon amount. Okay. So, let's see, extensive. And these are things that you'll be like, is that a property? Are you sure? Well, mass. Mass is a property of a chunk of matter you're looking at. You know, the property of this chair is it has a certain mass. But what is the mass of 10 chairs? Okay, it depends on amount. It does depend on amount. Another one is like, one of the things we'll be looking at is if you burn something, it depends upon kind of the conditions you burn it in, but what you're burning, how much energy you'll get out. Okay, it's kind of like set in stone, how much energy per gram. Okay, well, what property, how much energy you're going to get out? Well, it depends upon amount. Okay, so mass, energy released for combustion. Okay, it depends on amount. It depends. Okay, to me, physical change and chemical change kind of go along with physical property and chemical property. So if physical change has occurred, nothing new, no new substances were formed. Okay, chemical change has occurred, you got new substances. So if you take wax and you change its physical phase from solid to liquid, physical change. Again, physical change. This one actually is showing you, it might be hard to tell, but you have like a copper wire in there, a blue solution, and you see kind of this haze of gas. In order to think or to understand if a chemical change has occurred, hopefully you can kind of see the new substances would be that brown gas. Okay. New substances are formed during lighting of a match. Energy is released. New substances formed, the chemistry associated with browning food. Ugh. Now, my mom loves them like this, but my husband will not eat bananas that look like that. My mom will be like, oh, they're just ready. Okay. So, for instance, can it be undone? And this is a little bit of a tricky example, but like if you accidentally bleach your favorite shirt and it changes colors, you might be like, well, I'll go out and get a Ritz dye and try to get it the same color again. Well, you can do that, but it was transformed when it hit the bleach. Okay, so that's an example of a chemical change. Again, we have water in its liquid phase or water in its gaseous phase, physical change. The fact that plants actually produce carbon dioxide, that is a chemical change. Butter changing physical phase from solid to a liquid, that's a physical change. That's it. Okay, so I don't think we'll get through part 2, but we'll go ahead and start it. So part 1 homework is due when we meet again on Monday. And unlike my astronomy class, you guys have to actually give me a physical copy of it. But you know where the answers are, right? The answers are on campus. Okay. Let's see how far we get. And I got to remember that clock is a little slow. All right. In the chem lab, and actually in working problems in chemistry, working problems in physical science, you got to do some measurements. And one of the first things we're going to talk about are kind of some standards when you make those measurements. Again, this is kind of like, oh yeah, I kind of already knew that. Okay, so mass is, in general, how much matter there is in the container you're trying to measure. Length is the distance between 2 points. Okay, volume can actually go back to length. We're going to see here in a minute. But volume is how much space something occupies. Temperature is kind of something we already talked about. Temperature is a measurement of the amount of, this is my kinetic energy, because this is my atoms moving or molecules moving. Okay. All right. So how do we measure mass? These are standards, excuse me. We need to actually be able to, so we're all talking apples to apples across the world, we need to have a standard. And so with regard to the standard of mass, it goes back to a kilogram chunk of metal that is held under protection in Paris, okay? This actually was in the news a couple years ago. They chose an alloy that's very stable, so it shouldn't be losing mass. I think it's losing a little bit of mass, which makes things problematic. I was thinking about this lecture, when you go to gas up, right? At that gas station, you are counting on them having standardized or calibrated their pumps, their gas pumps, right? Then you have to think, well, they standardized their gas pumps, but who standardized the standardizers? Okay. There's what we call like a chain of command. There's like a chain of, like pedigree, how we all know it goes back to some standard. With regard to length, we actually can calibrate our, this is the yardstick, we can calibrate yardsticks in that based upon how light behaves, how fast it travels, which volume and goes back to length. Okay, you know that we can go from length to volume by saying how, with regard to an object, it's length times width times height. Okay, so those three things. With regard to time, we pick on the element cesium, one particular isotopic form of cesium, and its wavelength it emits. With regard to temperature, it's kind of an interesting thing. We pick on one substance, water, and we go to the triple point of water, which some of you guys, and you guys are going to see this value, 273.15, you're going to see that, and so maybe you guys know, it's the offset between the Celsius and the Kelvin scale. So 273.1 fifths, of that temperature interval between absolute zero and the triple point of water. That's how we calibrate our thermometers. Thank goodness our thermometers have already been calibrated. When we start to count molecules and count atoms, we're going to scale it up to the concept of a mole. And so the standard of a mole goes back to the element carbon and one isotopic form of carbon, carbon 12. If you have 1 mole of carbon atoms, which is, some of you guys know, 6.022 times 10 to the 23rd carbon atoms, then your mass should be 12 grams. So 1 mole, 6.022 times 10 raised to the 23rd power, which is a big number. But there's standards. You gotta have standards. This was that, I think it's an iridium sort of alloy that is under lock and key. Actually, this isn't the one under lock and key. This is a replica of that one. NIST are the folks that actually make or track the pedigrees of all the calibration of measuring devices. This just kind of shows you relative with regard to length. We have 1 inch, okay, 1 meter, which this is actually a meter stick, approximately a yard stick. I brought in this meter stick to kind of show you maybe what this looks like. We're going to talk more about the metric system, and there are some metric prefixes you're going to have to memorize. One prefix you don't have to necessarily memorize is the prefix deci. So up here we have decimeters, so DMs. This is 1 meter on this length, width, and height. So it's 1 meter on all 3 sides. In order to get the volume, you guys probably tell me it's length times width times height. So in this case, if all 3 dimensions are 1 meter, so I have 1 meter. When I multiply things together, I usually put them in parentheses like this, times 1 meter, times 1 meter. And of course, we multiply the ones times each other, we get 1. And we bring the meters times each other 3 times, which is 1 meter cubed. So that's where that came from. All this is saying is if you were to break it up into 10, each of these now is a decimeter. So up here you have 1 cute little decimeter squared. So, oh yeah, I was going to say, if I take this and have it as my length, my width, and my height, and make a volume like a box, that's more than 1 liter. And all it's saying, it is more than 1 liter. All it's saying is, so you guys can see this right here, 10, this right here. All it's saying is if I were to take this right here, which is a decimeter, and to go length, width, height, that is a liter. Okay. So the next little thing I brought is this. Is it adorable? Okay. So don't want to drop them all because I have them all back. But the way this works is a couple of these. So here's my centimeter, like a magician, see my little centimeter up there. Okay, so that's like 1 centimeter. Okay, so we have 1 centimeter by 1 centimeter by whatever that other dimension is, 1 centimeter. So that's 1 centimeter times 1 centimeter times 1 centimeter is 1 centimeter cubed. So that's a cubic centimeter. And as it turns out, the 1 cubic centimeter is equal to 1 milliliter. What's the abbreviation for milliliter?
Well,
ml, perfect. And it's actually case sensitive, so it's lowercase m and big L. Very good. Is that about it for the slide? Oh, that's an M. You got it. I thought this is kind of strange. It's an OpenStack slide. But this cubic centimeter is this right here. I think it's interesting to say, well, what's that look like next to a dime? Well, first off, I don't care about the volume of a dime. And second off, a dime is 1.8 centimeters diameter. And then, this is 1 centimeter. I don't know. But there you go. All right. Different glassware. What's the name of, starts letter P, what's the name of this glassware that has the green liquid in it? It is a pipette, so it has one calibration mark there. What's the name of this glassware? Graduated cylinder. Oh, I like this one. Beaker. Yep. This is a volumetric flask, the stuff with the yellow, and it's kind of like a pipette, and it has one calibration mark. And then this, you guys will be using it to burette. And it's kind of fun because you have a stopcock here to release liquid, and we have gradations on the burette. So here are some, oh yeah. These are the base units, and I'll kind of emphasize base. The one that throws me off is the base unit of mass is not grams, it's kilograms. That's about the only one that throws me off. In fact, if you've done much physics, you know that they'll break down, if you're dealing in the metric system, which you probably are, if you're doing science, it will be kilograms, won't be grams. So, where's your one? Okay. I'm going to go ahead and put an arrow next to the ones that you'll use a lot, and I'll count on you being able to commit to memory. There are 3 small ones, centi, milli, and micro. Now, it's not to say that in homework you won't have to or kind of mull around within those other prefixes. But centi, milli, and micro, those are all smaller than the base unit. And then one big one, and that's the kilo. So those 4 will really get you down the road, probably, when it comes time to your test. But the others you need to know. So if you're like me, some things that look pretty easy, and it is pretty easy when you think about it, but I have to concentrate. I always have to concentrate because I'm like, a kilogram, is that bigger than a gram or smaller than a gram? And then when I picture a kilogram, I'm like, well, that's pretty big. So then's when I start coming up with these equivalency statements that you, excuse me, are going to have to use. So I put grams are equal to kilograms. I'll be like, well, if I have 1 kilogram, I bet I have 1,000 grams, and that's right. But my point is just take your time with these, okay? Concentrate. Again, I told you kilo, centi, milli, and micro. The symbol for micro is this mu. It's the Greek letter mu. So if you had 1 micrometer, otherwise called a micrometer, you would have mu m, or micrometer. So of the 4, I'm having you at least know your way around for sure without the assistance of a table like this. Micro is the smallest, and it's 10 to the -6th. Okay, so for instance then, the way you would do that is I could put blanks micrograms is equal to blanks grams. Okay. I could say if I have 1 microgram, I have 10 to the -6th. And if you're like, I don't know what 10 to the -6th is, well then we'll get there. But you have to kind of know that it's 0.000001. Centi was one of the ones you need to commit to memory. So a little bit ago on the previous slide, 1 centimeter is equal to 10 to the -2nd meters. 10 to the -2nd is 1/100. Okay, so we all buy that. I'm going to show you a little trick, because when I come up with an equivalency statement for centimeters and meters, this isn't what I do. So if I were to I can take, as long as I do the same thing to both sides, I'm not a bad teacher, I can do it. So I'm going to multiply both sides by 100. That looks like this. Now, multiplying both sides by 100 then gives me this option over here where I have 100 in the numerator and 100 in the denominator. So I can rewrite that statement, and I have another statement about centimeters and meters. So my point is, and it's not a profound one, okay, but 1 centimeter is equal to 1/100th of a meter. Also, we could say there are 100 centimeters is equal to 1 meter, 100 centimeters and 1 meter. Okay, and again, the boxes are what we call equivalency statements. This is my equivalency statement thing, like this is the balance, and I have an equal sign here. Well, that's a good place to stop because I think we're bumping up against the hour. I did record this one, so I will post it, and we'll see how that goes. If you're curious for the post, you should be able to go to Canvas, and I'm going to update the Canvas site, and it's going to be the Twitter feed right there. Okay? Any questions? So when we meet Monday, we'll finish this part and start on part 3. So we have a long week, then we have a short week. Yay!